Thevenin's theorem establishes that any circuit can be simplified into an equivalent circuit with a voltage source and two resistors. Yes, even this one. This simplified circuit will be called Thevenin's circuit. So, what can you use this for? I got you. This is especially useful for scenarios where we wish to identify the current, the voltage, or power in a resistor of our choice. As I mentioned earlier, Thevenin's theorem simplifies our original circuit into one where we only have two resistors, one being the resistor that we want to analyze and the other being the equivalent resistor of the rest of the circuit, plus a voltage source, which is Thevenin's voltage. We can summarize the whole process in three steps, the first one being finding Thevenin's resistance, then the second one is finding Thevenin's voltage, and we finish off by creating the equivalent circuit with the found Thevenin's voltage and resistance. To show you how each step is done, we'll be analyzing this circuit. I'll keep things simple for now so it's easier to understand, but later in the video we'll tackle more complex circuits. To obtain the Thevenin's equivalent resistance, we first need to remove the resistor we want to analyze and identify the two terminals where we'll analyze the circuit. These will be our terminals A and B. Afterwards, we need to get rid of the voltage and current sources by applying the same method as we would in the superposition theorem, where we short-circuit the voltage sources and open the terminal of the current sources. Now that we have the circuit free of the resistor we want to analyze and the voltage and current sources, we just proceed to simplify the circuit to find the total resistance. Here we can see that resistors 1 and 2 are in parallel, so we can use the formula to obtain the equivalent resistance. As a result, we get the Thevenin's resistance, which will approximately be 9.1 ohms, since we have no more resistors left in the circuit. Moving on to the next step, we need to find Thevenin's voltage. We go back to the original circuit, with all sources active again, and the low resistors still removed. As we can see here, we have both a voltage and current source, which can make things a little bit more difficult. So in these cases, what I personally like to do is use the superposition theorem, where we find the voltage that each source provides and later adding or subtracting it depending on the direction of the current or voltage. We'll begin by analyzing the circuit with only the voltage source active. Remember, we basically eliminate the current source when we use the superposition theorem and start analyzing the circuit when affected by the voltage source. Now, how can we find the Thevenin's voltage here? I'll give you a few seconds and some options to analyze and think of an answer. The answer and way to find Thevenin's voltage will be by using the voltage divider. Why? Well, if you watch closely, the resistor 2 is in parallel with the Thevenin's voltage, which means the voltage in resistor 2 will be equal to Thevenin's voltage, because resistor 2 will represent the difference in potential between the terminal A and B. Knowing this, we can simply use the voltage divider for this mesh to find the voltage in R2. We multiply the input voltage, which in this case will be 10 volts, by the 10 ohms in resistor 2. Then, we divide this result by the sum of all resistance in the mesh. This will give us 3.95 volts for Thevenin's voltage when just analyzing the voltage source. Following the superposition theorem, now we want to analyze the circuit with just the current source active. Here, we short-circuit the voltage source, so this will be our circuit. As we did before, we can simplify the circuit by obtaining the equivalent resistance of R1 and R2, since they are in parallel. Here's an important thing. As we can see, no current and thus no voltage will flow through RA, since current follows the path of less resistance as shown on screen. Therefore, the Thevenin's voltage when the current source is active will be equal to 0. Given that the voltage is 0 when the current source is active, the Thevenin's voltage will be equal to 3.95 volts. Now that we have found Thevenin's voltage, we can move on to the final step, which is building the equivalent circuit with the Thevenin's resistance, Thevenin's voltage, and the original resistor that we wanted to analyze. Now we just use the voltage divider to find the voltage in R3. We multiply the input voltage by the 32 ohms and then divide by the sum of the resistors, which will give us the value of 3.07 volts for resistor 3. And there you go, that's the first circuit solved by Thevenin's theorem. Now that you understand the basics, let's move on to something a little more complex. Here we have a way more intimidating circuit, however, as I'll show you, it's not that hard to solve, it just takes more time. We'll begin by identifying the resistor we want to analyze. In this instance, it will be resistor 5. To find Thevenin's resistance, we open the circuit in the terminals of resistor 5 and remove the voltage and current source. Remember, if it's a voltage source, we short circuit it, and in the case of a current source, we open the circuit. Here we do basic circuit simplification and add R1 and R4 because they are in series. Now, RA and R3 are in parallel because they are connected to the same 2 points, so we'll just obtain the equivalent resistance so the circuit looks like this. Next, we just have to add these two to obtain Thevenin's resistance since they are in series. So we obtain the value of Thevenin's resistance, which is 12.72 ohms. Let's find Thevenin's voltage now. Just like we did with the first circuit, I'll use the superposition theorem and begin by analyzing the circuit with just the voltage source active. Remember, we open the circuit at the current source. Here we can transform the circuit into this. It's the same thing, but makes us see clearly the fact that the voltage of resistor 3 will be equal to Thevenin's voltage. This is due to the same concept we used in the previous circuit, where the voltage in the resistance is actually equal to the difference in potential between terminal A and B. So we just have to find voltage in R3 to know Thevenin's voltage. We can do this by using the voltage divider for this mesh. The input voltage will be the 40 volts that come from the voltage source, so we multiply that by the value of resistor 3 and divide the result by the total resistance in the mesh, which will give us a total of 18.18 volts for Thevenin's voltage when the voltage source is active. Let's do the same thing but now with the current source. We short circuit the voltage source and get the following circuit. You probably have already noticed that R1 and R4 are in series, so we just add them. Now the resistor RA is in parallel with R3, so we obtain the equivalent resistance. We basically did all of this when calculating the Thevenin's resistance. Now we can add RB and R2 since they are in series, obtaining the resistor RC with a value of 12.72 ohms. Now, how do we obtain Thevenin's voltage here? Well, if you have been very attentive, you probably already know the answer, which will be that we need to obtain RC voltage since it's the same as Thevenin voltage, due to it being the same as the difference in potential between these two terminals. Since 5 amperes will flow through RC, we just have to multiply the current by the resistive value, which gives us a total of 63.6 volts. Now we just have to observe the current direction for the voltage and current source so we can know if we have to add or subtract the voltages we obtain. As you can see here, we'll have to add them, so we obtain a final Thevenin's voltage of 81.78 volts. The rest is easy, we just have to build the equivalent circuit, so we'll have something like this. To know the value of the voltage in resistor 3, we simply multiply the input voltage, 81.70 volts, by the resistance 6 ohms, and divide by the total resistance in the circuit. This will give us 26.21 volts. Thank you for watching all the tutorials, and honestly, you really helped me by subscribing and liking the video. It just takes 2 seconds and lets me know you find these videos helpful. Again, thank you for watching.